Okay, so I stopped the last video, and since then Nolan has woken up. He is not eating anything. He's still in that waking up stage. So hopefully we can get through this video without him being too demanding. They are going to go play in the sand, but they're only like 20 feet away, so you might hear them. Okay. Oh, and I sprayed some fly stuff. Look, this fly stuff is pretty good. So if you have flies, this stuff's pretty good. There's the ingredients if you care. I was very, very hesitant because that EcoSmart brand, I've never had good luck with them. But this fly stuff's pretty darn awesome. Let's spray it again. There we go. Okay, so what we did last time was we did page 2 and the first part of page 3 of 4.1. And we did a lot of good stuff in this problem. This problem had a lot of good information in it. In order to find the zeros, x-intercepts, and graph, we first had to look at our function, factor it. We did not factor it because that is something you do in a later section. And we set each factor equal to 0. Then we plot all 3 of our real zeros because since they're real, they're all x-intercepts, so we plot those. It asks you for the y-intercept. Yeah, sure, why not? It just makes it a little bit harder to graph. So we plot the y-intercept, and then how do we graph from there? Because we just had those 4 dots. How do you connect them? Well, you have to look at the leading term. The leading term is x cubed. So it's a positive leading coefficient, which means the right side goes up. The the exponent of your leading term, which is technically called your degree. The degree of this function is 3, which is odd. And that means that the left side, the left in behavior, does the opposite of the right side, right? Odd exponent means one goes up, one goes down. So this side goes up, that side goes down. Now you just connect the dots. Wee. So the problem is what happens at these 3 dots, okay? At these 3 x-intercepts, does it cross through or does it touch, okay? Meaning, does it go up to that x-intercept and then come back down and then go back up to the x-intercept and then come back down? Because we could have easily had this situation. Goes through that x-intercept, through this x-intercept, so we had dot, 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 down. Okay, what if it had gone up, down, Why couldn't we have had that happen? Right? We still connected the dots. We still had this side go up, that side go down. Why is this not a solution? This is not a valid solution because our exponents of each factor were odd. This is a 1, a 1, a 1. X plus 3 to the first, x plus 1 to the first, x minus 2 to the first. And since they're all odd, that means that our graph crosses through the x-axis at each of those points. So this is touching. This is touching. The function here, if I wanted to write a function, if I wanted to write that as a function, that function would be x, what is that? A -3, so x plus 3 squared times x plus 1 squared, and then times x minus 2. That would be a function that could describe this graph, because when you have an exponent that's even, that's an even multiplicity. Boys, if y'all want to play there, you have to be quiet. X plus 3 squared, that square, and x plus 1 squared, those are your multiplicities. Those exponents are your multiplicities. And that's what we're going to see later on down here. But this would be a function that could describe that graph. Since ours are all to the first, to the first, to the first, we know that they're all going to cross through at those points, okay? Okay, now I want to look at example 2. I really urge you, actually, after we do this example, come back up to this one and listen again, see if you can understand what this is and why I knew this right away. Okay, so example 2. Determine whether 2 and -5 are zeros. How do you determine if 2 and -5 are zeros? Well, this is actually a really easy problem. Remember how when you plug in the number, you'll get back 0? Where do I have that at? I have it on, oh, I already saved it. I put it away. I know y'all aren't 2303, but I can't find my Thor folder, which is the one that I would use for this class, because Thor is amazing. Right there. On the quadratic formula in roots and zeros, we say x equals c is a 0 or root if when you plug that number in, you get back 0. So if we're asking, is 2 a 0? Well, plug 2 in, and if you get back 0, then yes. So we're going to come back to our, I'm going to put these away so they don't fly away. We're going to come back to our worksheet, and we're going to say, okay, is 2 a 0? I don't know. Let's take our function and plug in 2. P of 2 equals 2 cubed plus 2 squared minus 17 times 2 plus 15. What is that? And then I'm going to check -5. I'm going to plug in -5, so I have -5 cubed plus -5 squared minus 17 times -5 plus 15. What is that? What is that? If it equals 0, then yes, that x value is a 0 of the function. Okay? Let me see. Can I do this in my head real quick? Not really. I'm like, oh. So we have, in that first one, we have, we have 8 plus 4 minus 34, and then plus 15. I get -7 back right here, okay? I get -7 back for this one. So no, that's not a 0. I might check that again. 8 plus 4 minus 17 times 2 plus 15. Yep, still -7. Okay, so that is not a 0. Now -5. -5 is -5 cubed is going to be a -125 plus 25. Whoops. Plus 25, and then minus 17 times 5. I'm not going to pretend to know what that is, so I have plus 17 times 5. Why did I do plus 17 times 5? Because it's a -17 and -5. Oh, and then add 15. I'm at -15 right now, so add 15 would make it 0, right? Bam, 0. So this is 0. So which one is a 0? Well, this one is not. This one is. Okay. Yay! And that's it. So if you want to know whether or not something is a 0, you could just plug it in. Now there's another way of doing it using synthetic division, but we're not going to get to that until maybe the next section. Maybe the section after that. So let's go on to example 3. So example 2 is just kind of like one of those things you just throw in there. Hey, this applies as well. Example 3 is looking at multiplicity. So we have this function. It's already factored for us, but I'm going to rewrite it. Okay, I'm going to rewrite it as 5 x minus 2. But see this x minus 2, x minus 2, x minus 2? I have it 1, 2, 3 times. X minus 2 quantity 3 times x plus 1. I'm going to write it like this. If I were to use, damn fly, darn fly, sorry. Get out of here. I have a big red right next to me, and apparently flies love big reds because he just went all up in there. He came out really quickly though. So if I want to find zeros, sorry about that. If I want to find zeros, I take my function, and what do? I factor it. It's already factored. I set each factor equal to 0. So that means I would set x minus 2 equals 0. X minus 2 equals 0. X minus 2 equals 0. I'm really bored of that. How many do we have? 1, 1, 1, 1, 1, 1. And then x plus 1 equals 0. So I solve each of these, and what do you get? You get x equals 2, x equals 2, x equals 2, and then x equals -1, right? You have x equals 2 3 times. So you say your 0 is x equals 2. with a multiplicity of how many do you think? How many do you have? Of 3. So I'm going to grab that weird golden color. So multiplicity of 3, remember how I rewrote it? How many factors did we have? We had 3 factors. 1, 2, 3. 3 factors. Since we had 3 factors, we could write it out 1, 2, 3 times, or we could just solve x minus 2 one time and say it's a multiplicity of 3. Okay, so we have, how many zeros do we have? That's a good question. How many zeros do you have? You could say, well, if I'm going to plot them, I have x equals 2 and x equals negative 1. I have 2 x-intercepts. And I would say, yes, you are correct. You have 2 x-intercepts. But how many zeros do you have? How many zeros do you have? You have 4 zeros. 4. How do you know you have 4 zeros? Where are the 4 zeros? I only see 2. 1, 2. No. You see 2 real zeros. You have 2 real zeros. Okay? But one of them is a multiplicity of 3. So you really have 4 real zeros. So what is this multiplicity of 3? What do you do? How does this affect your graph? Well, since that is odd, your graph will cross at 2. So anytime you have a factor that repeats, it's going to have a multiplicity of however many times it repeats, okay? So this repeated 3 times, so we had a multiplicity of 3. But we still had 4 zeros. Okay, so now how do we connect the dots? What's the leading coefficient and what is the leading term? What's the degree? This is super hard. It's actually not that hard, but it is. So what I'm going to do is I'm going to grab my yellow marker and I'm going to highlight this first factor. That first factor, what's the degree of that first factor? Well, first I'm going to write down this 5. 5 times. That first factor has an x in it, right? It's not x squared minus 2, it's just x minus 2. The second factor is an x. The third factor is an x. The fourth factor is an x. So if I were to multiply all these together, it would be a whole lot. But if I multiply all of them together, I would end up with a 5x to the 4th, right? You have 1, 2, 3, 4 x's. So you have 5x to the 4th, and that would be your leading term. So 5x to the 4th is your leading term. 5 is positive, so what does that mean? A positive 5 means it's going to go up on the right. X to the 4th, an even degree says the other side's going to do the same, up. Then we look at 2 and negative 1. Are those multiplicities odd or even? Well, x plus 1, we only had one of those, right? It was just to the first power, so it's going to cross through there. So it's going to come down. I'm going to draw this in a different color. I can never, whenever I draw my in behavior arrows, I can never match them up. The fact that I matched them up here was really, really exciting. So I'm going to draw, it's going to go up. And then over here, when x is 2, I have a multiplicity of 3, so it's still going to just cross through. Looks kind of like I can use that arrow. There we go. There we go. So now, technically, we don't know what happens right here. It could have looked like this, right? It could have looked like this. Cross through, and had a little bump in the middle. We don't know. We don't know. So all we know, we don't know what's happening in here unless we do a little more digging, okay? That's where calculus comes in. You take the derivative, set the derivative equal to 0, and you find out where it has flat spots. That's where your slope is 0. Slope is 0. Slope is 0. Okay? So here, my slope is 0. So my slope is 0 just one time. In calculus, when you take the derivative, set it equal to 0, you might end up with 3 answers. And that would say, hey, your graph looks like this, not like this. Okay? But we're not in calculus. So we just have question mark, question mark, question mark. I don't know. This is how I'm going to connect the dots. Okay? Okay. Next, let's look at example 4. Example 4, ooh, he's fun. So example 4, I'm going to ask first, what is the leading term? What's my leading term here? I'm going to stop using pencil because I have a feeling that it's not going to come through very well, especially when I try to scan this and send it to you. There we go. So here I see x minus 1 times x minus 1. Both of those are the same. X plus 2, x plus 2, both of those are the same. So what I see is I see a function, f of x is negative 1 times x minus 1 squared times x plus 2 squared. So I see I have a 0 at x equals 1 and a 0 at x equals negative 2, and both have multiplicities of 2. And they both have multiplicities of 2 because of that, okay? Because they're both squared. So the question, when we're trying to graph, the question is what is the leading term? What's our leading term? So my leading term, if I was looking at multiplying all of this out, I would have a negative 1 times, from my first factor, I have x. From my next factor, I have x. From my next factor, x. Next factor, also x. So my leading term is negative 1 times x to the power of 1, 2, 3, 4. X to the 4th. So we have a very, very similar graph to up here, right? So now I'm going to go ahead and draw negative 2, 1, 2, positive 1. There we go. So that's all that I need on that. I'm going to go ahead and do my end behavior. My end behavior, since it's a negative 1, I know my right side is going to go down. Since it's an even degree says both sides do the same. Same on left. Okay, go down on the left. And then I'm going to plot my 2, plot my 1, and how do I connect the dots? Multiplicity of 2 says the graph will touch. The graph touches the x-axis. Okay, the graph touches the x-axis. It really aggravates me whenever I do like capital, 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 and then all of a sudden I have a lowercase. Why? I don't know. So it's going to come up and it's just going to touch. It's going to come back down. It's going to go up and it's going to touch. Go back down. Okay. And that would be my graph of my function. Yay! So now you can go back and kind of rewind the lecture and see how would you know, how did I know what this function could be if the graph potentially looked like this. See how it's touching at negative 3, touching at negative 1? That means that negative 3, the 0 of negative 3, would have to have an even multiplicity. The 0 at negative 1, if it touches, would have to have an even multiplicity. And if it crosses at 2, that would have an odd multiplicity. Okay. And maybe you should expand on a couple more ideas on there. Okay, so let's go on to the next page. I'm already at 19 minutes. You know what? These are harder. So I'm actually going to pause on these and I'm going to put these in another video, okay? So these are harder just because now we actually have to factor them. And factoring by grouping is something you might want to revisit. We haven't done grouping in this class. But here, what you do is you look at the first two and you look at the next two. And when you factor by grouping, maybe I'll start this example. We factor out, we just look at these two and go, okay, what's common between these two? I can take out an x squared, right? I'm going to take out an x squared from the first and x squared from the second. And what am I left with? When I take out an x squared from x cubed, well, x squared times x is x cubed. Then minus 2 times x squared. Well, if I'm taking out x squared, then I just have a minus 2. Next, when you factor by grouping, you need this x minus 2 to be repeated, okay? You need it to be the same over here, x minus 2. So what can we take out to leave us x minus 2? A lot of people say 9. 9 is almost correct. Why is 9 incorrect? Because if you take out a 9, you're going to distribute it and you'll get back a positive 9. Do we have a positive 9x? Nope. We'd also have a negative 18. Do we have a negative 18? Nope. So do we take out positive 9? No! We take out negative 9. Negative 9. So you take out negative 9. And then after that, whenever you finish factoring, I'm going to write down this x minus 2. He basically just follows along. And what I'm going to do is, since I can highlight now, I'm always talking about I can't highlight the whiteboard. We're taking out that x minus 2, right? So what do we have left over? We have x squared from that first term and negative 9 from the second term. So this is almost our factorization. Why is it not our factorization? Hold on one second. Champ, that is a B. Do not eat the B. Don't eat the B. He's part lab. They said he's all lab. But he's not very smart. Okay. Here, we're almost done. Okay, we're almost done. But this right here, this x squared minus 9, when I look at that, I see the difference of squares. And what do the difference of squares factor to? Conjugate pairs. So this is really going to be x plus 3 times x minus 3 times x minus 2. Well, this problem wasn't very hard at all. You just had to know factoring by grouping. So now, if we're just trying to find the zeros, now we factored it. Now we just set each factor equal to 0. So now we set each factor equal to 0. So we get x plus 3 equals 0, x minus 3 equals 0, x minus 2 equals 0, and we get negative 3, positive 3, and positive 2. Yay! You can hear Nolan in the background. That's like my only sound effect. I don't know if he got it from me or not. Okay, if you're wanting to graph this, I see it's a positive x cubed, which means this side goes up, this side goes down. They're all first powers of the factors, so they're all multiplicity of 1, so we just connect the dots like that, and that's it. Yay! See, not a very pretty drawing, but it gets the job done. So I'm actually going to stop there because this one's maybe a little bit harder.